Let's take a look at Chapter 19, Testing Hypotheses about Proportions. Hypothesis testing is a huge part of the AP statistics curriculum and statistics in general. They have several good examples here at the beginning in your textbook. So I just wanted to go through that quickly before we jump into their PowerPoint notes. In case you didn't know, well, okay, come on. Technically, Fenwick is in Middletown. Middletown has still a steel industry that operates. Ingots, I know that's hard to read there at the beginning. Ingots are huge pieces of metal, sometimes weighing more than 20,000 pounds, made in a giant mold. They must be cast in one large piece for use in fabricating large structural parts for cars and planes. As the liquid metal cools, however, cracks can develop on the surface of the ingot, which can then propagate into the zone required for the part, compromising the integrity of the entire ingot. Airplane manufacturers especially insist that metal for their planes be defect-free, so the ingot must be made over if any cracking is detected. Even though the metal from the cracked ingot is recycled, the cost runs into tens of thousands of dollars to recast one, not to mention the wasted energy. About two-thirds of all aluminum ingots produced in the U.S. use a process called direct chill designed to reduce recasting. Metal manufacturers would like to avoid cracking if at all possible, but the casting process is complicated. Not everything is completely under control. It's estimated that about 5% of aluminum ingots need to be recast because of cracking. That rate is dependent upon the size of the ingot cast. In one plant that specializes in very large ingots, over 30,000 pounds, about 20% of the ingots have had some kind of a surface crack. In an attempt to reduce the cracking production, the plant engineers and chemists recently tried out some changes in the cracking process. Since then, 400 ingots have been cast, and only 68 of them, which translates to 17%, have cracked compared to 20% earlier. Has the new method worked? Has the cracking rate really decreased, or was the 17% just due to luck? Is the 17% cracking rate merely the result of natural sampling variability, or is this enough evidence to justify a change to the new method? People want to make informed decisions like this all the time. Does the new website design increase our click-through rate? Has the Click It or Ticket campaign increased compliance with seatbelt laws? Did the Super Bowl ad we bought actually increase sales? To answer such questions so that we can make intelligent decisions, we test hypotheses. Hypotheses are working models that we adopt temporarily. To be a good scientist, to be a good statistician here, you have to remain emotionally neutral, even when, especially when you're doing research. Our starting point is always something called the null hypothesis. Now, again, this is got some special symbols here. Yeah, like that's shocking in a math class. H sub 0 is the symbol that we use for the null hypothesis. It specifies a population model parameter of interest and proposes a value for that parameter. Okay, we usually write the null hypothesis, H sub 0, colon, parameter equals hypothesized value. Immediately after we establish that, we come up with something called the alternative hypothesis, H sub A. Contains the value of the parameter that we consider plausible if the null hypothesis is wrong and we reject it. Our question of inquiry determines our alternative hypothesis. If we hope to find evidence that a new medication decreases the percent of an infection, our alternative hypothesis will be that that proportion is less than the current percent. The null hypothesis specifies a population of parameter of interest and proposes a value, like I just read like 15 seconds ago. We might have, for example, the null hypothesis, the proportion is zero point 0.2. Okay, going back to the aluminum ingots example. Okay, 20% of theirs cracked. We want to compare our data to what we would have expected given that the null hypothesis is true. We can do this by finding out how many standard deviations away from the proposed value we are with our sample data. Then we ask, how likely is it to get results like we did if the null hypothesis were true? All right, they come up with, they go down this particular path here with jury trials. To prove someone is guilty, we start by saying they are innocent. We retain that hypothesis until the facts make it unlikely, beyond a reasonable doubt, that the person is innocent. Then we reject the hypothesis of innocence and declare the person guilty. Okay? This is the same kind of process that you need to do with hypothesis testing. We start off with a null hypothesis. We examine evidence until we can decide whether that null hypothesis is false. And if we can reject that null hypothesis, then that'll lead us to interesting statements. Okay, so we begin by assuming that the null hypothesis is true. We consider whether the data is consistent with that hypothesis. And if it is consistent, we're going to retain the hypothesis with which we started. Ooh, that's bad grammar. Um, if the data is not consistent with the null hypothesis, then, like a jury, we ask whether they are unlikely beyond a reasonable doubt. So the insight here is finding a p-value, the probability of this happening. Okay, and again, we've, I think, done this a little bit here. What you're going to have to learn how to do in 19, and we will continue on into 20 here, is putting things in the right sequence and doing the right kinds of calculations. We can use the model proposed by our hypothesis to calculate the probability that what we've seen from our sample could happen. It's just the probability we're looking for, how surprised we are to see the results. If the p-value, the probability that this is just statistical variation, if that p-value is low enough, then we will reject the null hypothesis. Note how they put that in bold print. That is a key phrase that you need to use. If the p-value is low enough, we'll reject the null hypothesis, saying that, okay, what we got from our sample data would be very unlikely if the null hypothesis was true. When the data are consistent with the model from the null hypothesis, the p-value is going to be high. Now that's a relative term, and we'll talk about that. And we are unable to reject the null hypothesis. Okay? So here's your other key phrase. It's going to be binary. It's one of these two. Either the p-value is low and we reject the null hypothesis, or the p-value is too high. We can't claim that we've proved that the null hypothesis is true. Instead, here's your phrase, we fail to reject the null hypothesis. It's either reject the null hypothesis or fail to reject the null hypothesis. Yeah, that almost sounds like a double negative, but be careful. There's a good reason for this. Again, we'll come back to that later. If the evidence is not strong enough to reject the presumption of innocence, the jury returns with a verdict of not guilty. Now, again, that's careful phrasing there. The jury does not ever say that the defendant is innocent. The jury says the verdict is not guilty. There's not enough evidence to convict, to reject the null hypothesis of innocence. The defendant, in fact, may be innocent, but the jury has no way to be sure. Said statistically, we failed to reject the null hypothesis. We never declare, oh, look at that, they put it in bold and underlined it. We never declare that the null hypothesis is true because we don't know. Just one survey, one set of statistics isn't going to be enough to prove that the null hypothesis is always going to be true. Sometimes we say that the null hypothesis has been retained, but again, that's not the common phrase. It's either reject the null hypothesis or fail to reject the null hypothesis. And again, continuing with their legal analogy here, burden of truth is on the prosecution to test the hypothesis of innocence. Um, the burden of truth is on an unusual claim. We're saying the null hypothesis is the ordinary state of affairs, so the alternative to the null hypothesis is what we consider to be unusual. All right, so let's check and make sure that we're on the right path here. The research team wants to know if aspirin in a certain dosage, I guess, helps to thin blood. The null hypothesis says it doesn't. They test 12 patients, observe the proportion with thinner blood, and get a p-value of 0.32. They proclaim aspirin doesn't work. What would you say? With a p-value of 0.32, that's relatively high. Okay, we're saying that if similar tests were run with a sample of the same size from a similar population, we would get that same proportion, 0.32 or 32% of the time. That doesn't really seem all that rare. Um, it's not really likely, but wow. We cannot conclude that the null hypothesis is true at this point. We can conclude only that the experiment was unable to reject the null hypothesis. They were unable, on the basis of 12 patients, to show that aspirin was effective. Okay, so a p-value that's high, we fail to reject the null hypothesis. Number two, an allergy drug has been tested and found to give relief to 75% of the patients in a large clinical trial. Now the scientists want to see if the new, improved version works even better. What would the null hypothesis be? Well, in this case, the null hypothesis, again, we would write that as H sub 0. Hopefully you're learning how to the proper symbols there. The null hypothesis, P equals 0.75. Number three, the new drug is tested and the p-value is 0.0001. What would you conclude about the new drug? Considering how small that p-value is, now again, you take that, again, it's a probability there, turn that into a percentage. The percentage that of time that this would happen, and it would be explained just by sampling variability, is 0.01% of the time. What would you conclude about the new drug? I would say we have very strong evidence against the null hypothesis. In the formal hypothesis testing write-up that you would do, you would use the phrase, because the p-value is so small, 0.0001, we would reject the null hypothesis. That's the key phrase that you would use there. All right, let's talk about the alternative hypotheses and the yay Department of Redundancy Department, the alternatives. There are three possibilities for our alternative hypothesis. Either this parameter that we are trying to estimate here, again, for the entire population, that's our definition of the word parameter, is less than the hypothesized value. Again, the hypothesized value is what we put in the null hypothesis. That's always the parameter is equal to this value. So either the alternative hypothesis is the real value is less than what we said in the null hypothesis, it's simply not equal to, or it's greater than what we said in the null hypothesis. So if it's not equal to, this is called a two-sided alternative. And hopefully from the graph there, you can see why. If we're saying it's not equal to, the p-value here is the probability of deviating in either direction from our null hypothesis value. Okay, so there's a couple of different ways that you can do that with the calculator there. The easiest way is to use um, two different z-scores, or again, use a positive z-score and a negative z-score, rather than going all the way down to negative infinity or all the way up to positive infinity. That would be finding a one-sided alternative. And then again, if you use the not equal to value in your alternative, you would double that. I find it easier with the calculators you have, with the technology that's available, just to put in the two different z-scores and go from there. Again, just greater than or just less than, those are called one-sided alternatives. Okay, so in there you would use, with the graph that's down at the bottom there, they're showing you would go find the p-value here going from negative infinity to whatever the z-score was that you found. All right, so writing it out, there are four basic parts, the way they're describing it here, to a hypothesis test. Number one, you have to write out, be very, very explicit, what your hypotheses are. Number two, model what happens. Number three, the mechanics. This is really the calculations of it, the arithmetic, if you will. And then four, being smart about how to interpret those numbers that you got in step three and draw a very specific, very accurate conclusion. So again, step one, part one is writing out both of the hypotheses. Start with the null hypothesis, and in whatever context it is, the alternative hypothesis. Okay, that's not too hard to do. Use the right terms, use the right symbols. The second part here is modeling. To plan a statistical hypothesis test, you specify the model that you're going to use to test the null hypothesis and the parameter of interest. Okay, you've got to be explicit in writing this out about what your population is. All models require assumptions, so state the assumptions and check any corresponding conditions. You must write this out. You can't just say, oh, I checked the conditions necessary and everything passed. You have to give evidence. And your model step should end with a statement, okay, because the conditions are satisfied, we can model the sampling distribution of the proportion here with a normal model or a binomial model or whatever kind of model you think is most appropriate. It might be the case that your model step ends with, because the conditions are not satisfied, I cannot proceed with the test. If that's the case, then you've got to stop and reconsider maybe the null hypothesis, maybe a different model, something that can pass those conditions there. I don't think in the 2020 AP statistics test that you're going to get that because the conditions are not satisfied. I cannot proceed with the test, and that's it. No, I don't really think you're going to get that one this year. Each test we discuss in the book has a name that you should include. Um, okay, tests about proportions are called one proportion Z test. Again, that's a phrase that you need to know. That's a phrase that you will need to include in your answers, telling the reader what you went through and did. That's still part of the model step. Okay. So for a one proportion Z test, okay, this should look familiar to you, although you might need to dig a little bit more into our lovely formulas there. We're going to find a Z score. Okay. So we're going to take P hat, Z equals, do you see this in the numerator here? P hat is going to be the proportion that we got from that's our statistic. Okay, P sub 0 is the value that's going to come from the null hypothesis. And then we're going to divide by the standard deviation of P hat. Well, again, we've talked about that for proportions here. We're going to take P times Q divided by N. Okay, P is going to be that value from the null hypothesis. Q is going to be its complement. N is the sample size. Okay. When the conditions are met and the null hypothesis is true, this statistics follows the standard normal model. So that's what we use to get our p-score. Under mechanics, we place the actual calculation of our test statistic from the data. Now again, slightly different formulas, slightly different test statistics. It's good to know the formulas. You'll have on the exam that formula sheet that you can refer to. You're going to plug things into the calculator, but on the test, you're going to write out what numbers you plugged into which formula. And again, you're going to write it out more like this, and you're not going to write out what you typed in onto your calculator. You're not going to use TI speak. The ultimate goal of the calculation is to get a p-value. The p-value is the probability that the observed statistical value could occur if the null model were correct, or even more extreme value. If the p-value is small enough, we reject the null hypothesis. If the p-value is too big, we fail to reject the null hypothesis. This is a conditional probability. It's the probability that the observed results could have happened if the null hypothesis is true. And then you'll write out your conclusion in step 4. And again, the phrasing here is critical. First part of the conclusion is always a statement about the null hypothesis. Either we reject the null hypothesis or we fail to reject the null hypothesis, and then you tie that decision to your p-value. Now we get into something called a significance level, and it really doesn't show up well on this font. This thing right here is supposed to be the lowercase Greek letter alpha. Okay, that's our significance level. There's more about alpha to come in chapter 20, but for right now, I hate how they use the percent here. I'm sorry, I should have changed that. One of the standard significance levels here is 0.05 or 5%. If our p-value is bigger than 5%, we fail to reject the null hypothesis. If our p-value is less than 5%, then we reject the null hypothesis and imply that our alternative is the case. How small the p-value has to be rejected is context dependent. Now, again, that 5% level there is a standard. Sometimes they might throw at you a different significance level, so you have to be prepared for that. Your conclusion about any null hypothesis should always be linked to that p-value of the test and accompanied by, maybe even accompanied by, a confidence interval to report the size of the effect. Okay, again, confidence interval was in an earlier chapter. And again, for the 2020 exam, we'll talk about this, but I'm guessing a hypothesis test and including a confidence interval is very highly likely that you're going to have to do this. The American Statistical Association recently published a statement about p-values. It recommends 6 principles how to properly interpret p-values. They can indicate how incompatible the data are with a model. It does not measure the probability that the studied hypothesis is true or the probability that the data were produced by random chance alone. The applications here should be based only on whether a p-value passes a specified threshold. Proper inference requires full reporting and transparency. Statistical significance does not measure the size of an effect or the importance of a result. And all by itself, a p-value does not provide a good measure of evidence regarding a model or a hypothesis. Now, you're not going to be tested on those, but this is here to help you understand what a p-value will do and what it won't do. All right, so let's check this. How well are you understanding? A bank is testing a new method for getting delinquent customers to pay their past due credit card bills. The standard way was to send a letter costing about 40 cents asking the customer to pay, and that worked a whopping 30% of the time. They want to test a new method that involves sending a DVD to customers, encouraging them to contact the bank and set up a payment plan. Developing and then sending the video costs about $10 per customer. So let's answer some questions here. What is the parameter of interest? What are the null and alternative hypotheses? So the parameter of interest here is the proportion, usually lowercase letter p, of all the delinquent customers who are going to pay their bills. Okay, again, with that, be as specific as humanly possible. Don't just say bank customers. Don't even stop with delinquent bank customers. It's the proportion of all delinquent customers who will pay their bill if they're reminded. The null hypothesis here, we're going to say H sub 0 colon P equals 0.30. Okay, so we're starting with what we have at 30%, so 0.3. That's our null hypothesis. The alternative hypothesis is this new way is going to work better. So the alternative hypothesis is going to be P is greater than 0.30. Number 5. The bank sets up an experiment to test the effectiveness of the DVD. They mail it out to several randomly selected delinquent customers and keep track of how many actually do contact the bank to arrange payment. The bank's statistician calculates a p-value of 0.003. What does this p-value suggest about the DVD? Now, if we're going to use our standard 5% or 0.05, here we have 0.003. This very low p-value leads us to reject the null hypothesis. There is very strong evidence that the DVD is more effective in getting people to start paying their debts than just by sending out a letter. Number 6, the statistician tells the bank manager that the results are clear and they should switch to the DVD method. Do you agree? And what else might you want to know? Well, we know that there is strong evidence to suggest that this proportion is in fact greater than 0.30% using the DVD. But thing is, we don't know how much higher than 30% this new proportion is. What else might we want to know? How about a confidence interval to tell whether the increase in payments offsets that additional cost? Again, the letter was 40 cents, the DVDs are $10, and the repayment might have gone up, but by how much? And is it worth the added expense? All right, what could possibly go wrong? Hypothesis tests are so widely used, and oh, how about a little opinion here from our authors? Widely misused. The issues are continued here, and they talk about it in chapter 20. Um, some of the things. Don't base your null hypothesis on what you want to see or what the sample statistic tells you. Think about the situation you're investigating. Develop the null hypothesis appropriately, independently. You've got to approach these things as in, oh, the new drug is not more effective than the one that we have, or this new method is not going to be any better than the one we currently use. And then you hope that your statistics disprove that null hypothesis. Don't base your alternative hypothesis on data either. Again, think about the situation. Do we want the new drug to be more effective? Do we want this new drug to reduce infection rates? Okay, so greater than, less than, or the not equal to. Don't make your null hypothesis on what you want to show to be true. Again, what you're hoping to see as a researcher, that comes out with the alternative hypothesis, not the null. You can reject the null hypothesis, but you're never going to accept it. You're never going to prove that the null hypothesis is true. Um, Again, randomization, independence, sample size that's large enough. Those are some of the conditions you need to justify the use of a normal model. And again, you can refer to previous notes about conditions. I love the fact that here's this next bullet point, and all bold, never accept the null hypothesis. We can reject it, we can fail to reject it, never accept it. If you fail to reject the null hypothesis, don't think that a bigger sample is going to be more likely to lead to rejection. Each sample is going to be different. A larger sample won't necessarily duplicate the current p hat. Don't say we prove that the alternative hypothesis is true. Strong evidence is not a certainty. Okay? If we reject the null hypothesis, it may imply that the alternative hypothesis is true, but don't say that we proved it. If you fail to reject the null hypothesis, they said that already. Sorry. So, summarizing. We use a random sample to test a hypothesis about something of interest. And again, hypothesis tests and confidence intervals, you should be able to link those two. A hypothesis test helps us to make a decision about the plausibility of a value of interest about the population of interest, a parameter. A confidence interval estimates a whole set of plausible values for the parameter. Okay, so here's the big distinction here. Hypothesis test helps us make a decision about the plausibility of one value. A confidence interval estimates a whole set of values that are plausible for this parameter we don't know. Again, you should be able to write null and alternative hypotheses. What kind of a test? Do the calculations, find your z-score, find your p-value, And then, depending upon how big or how small, again, relatively speaking, that p value is, then we should make a conclusion. And again, this one here is just highlighting the four different portions of a hypothesis test. Um, Again, they're just trying to re-emphasize here the form of the null hypothesis, the form of the alternative hypothesis. Um, for conditions, independence, randomization, the 10% condition, again, that means that we're taking a sample size that's not more than 10% of the entire population. And then the success failure condition, make sure that you're writing that out on the AP exam, that you're taking your sample size times p sub 0, in this case from our null hypothesis, and n times q, and making sure those are both greater than 10. Then we can use a normal model, perform a one proportion z-test. Again, our formula's there, you know those, and they're on the sample sheet. If the p-value is very small, it's highly unlikely that we would get the results of ours if the null hypothesis were true. We reject the null hypothesis and say there's strong evidence to suggest the null hypothesis is false and the alternative hypothesis might be true. But if the p-value is too big, again, we fail to reject the null hypothesis. Not enough evidence to say the null hypothesis is false. All right, finally, you have to write out that you checked your conditions. They will not remind you, but you're expected to do that. Write your conclusion carefully, make sure that you tie it in with the p-value. And then finally, accepting the null hypothesis will always cost you points. Okay, so again, take a look at the assignments. We'll go through the normal routine here, and we'll get you guys ready for this.